Okay, and we're live. Welcome back. We'll be going through a couple problems from 2010 and 2005 today. I had a couple requests, again, some more problems for volume by cross-sections and separable differential equations. Also pulled a few more for curve sketching. So, first one. I've got this region R that's shown here in the first quadrant. It is bounded by 2 root x, the horizontal line y equals 6, and the y-axis. The first thing we need to do is figure out what the area of R is going to be. So what do we have to do here?
Integrate from 9 times 6 minus the integral of 2 root x from 0 to 9.
Okay, so what you just did was you got this box then, and then you took out all the white space, right?
Yeah.
Cool. I'm going to do the same thing, but I'm going to set it up just a little bit differently. So, if I wanted to get the area between any two curves, we could integrate our top curve minus our bottom curve from start to finish. So if I do that, this will be the integral from 0 to 9 of 6 minus 2 root x. That's 6 is our top function up here, y equals 6, and then our bottom function is 2 root x. And the math will end up being the same thing that you just did. So we'll take the whole area of this box and then cut out all the area in yellow that's underneath the bottom function. So same idea, but we can set that up in one integral. Okay, so if I integrate this, what's going to happen?
6x minus 2 ln x. Oh no, 6x minus 2 x 3x to the 1/2 power.
Okay, well, hold on. So this root x is the same thing as x to the 1/2 power. So what happens when I integrate?
The x turns into 1.5 power.
The x will become x to the 1/2 plus 1, or the x to the 3/2 power.
And 2 over 1.5, which is 4 over 3.
4/3, perfect. Okay, and then I had bounds from 0 to 9, so we're going to plug those in. If I plug in 9 over here, what will I get? What happens if I plug in 9?
54 minus 9 to the point 12 54 plus 12 minus 12.
Okay. If you wanted to do that in your head, this 9 is going to be over 2, so that's the square root of 9 is 3, raised to the 3rd power is 27, divided by 3 is 9, times 4 is 36. So this is the same thing as 54 minus 36, or 18.
Oh, got it.
And then when I plug in 0 to both of these, it gets 0. So I didn't write minus 0, I probably should have, but I was kind of running out of space. So if I do my upper bound minus lower bound, our total ends up being 18. Okay, then I want to write but not evaluate an expression that gives the volume of the solid when R is rotated around the horizontal line y is equal to 7. So y equals to 7 is somewhere up here. Is this going to be disk method or shell method?
So it's revolving against the top line, right?
Right.
It's disk method.
Cool, so this is this method because we're rotating around a horizontal line. Anytime you're rotating around a horizontal line, you can use this method and you won't have to change your variables. You can use shell method if you're rotating around a vertical line, and then you won't change your variables that way. So this is this method. For this method to work, our general form for this method is pi times the integral of r1 squared minus r2 squared in terms of x from a to b. What is r1?
Nine. 6.
Okay, so one of my radii is going to be 6, but that's actually going to be my smaller radii. So that'll end up being r2. R2 is going to be my difference between 6 and 7. So if I do 7 minus 6, that'll give me the distance to my inside function, which is here. For my r1, I'm going to change colors.
2 root x.
It's going to be based on 2 root x, but I need my distance to the axis of rotation. So what's the distance from 2 root x to the axis?
7 minus 2 root x.
Perfect. Okay, so what I'm really doing is this. We're creating 2 disks that have the radius that I'm showing right now. So like this and like this. And we are cutting out that inside disk. Redraw that just a little bit. We are cutting out our inside disk from our outside disk. So my R1 is based off of our distance to the outermost function. So it's not top or bottom, it's which one is the furthest away from our axis of rotation. Which for us, the one that's the furthest away from our axis of rotation is the 2 root x one. And my difference between y equals 7 and 2 root x is going to be my radius. Our innermost function is what I'm going to cut out of it. That radius is going to be 1 for us. That's 7 minus 6. Okay, so we can set that all up. So I'm just going to move everything down here. If I wanted to get the volume, I could say the volume is equal to pi times the integral from a start point to end point. So that's from x equals 0 to x equals, what was that for us? X equals 9. Of our r1, 7 minus 2 root x minus our r2, or 1 squared. That's all times dx. Do we have to solve this? No. Okay. Right, but do not evaluate. So we're done there. Okay, and then part C. I guess I'll come back and erase this so we can redraw. So part C says we're going to build a new volume by cross-sections instead. Each cross-section forms a rectangle perpendicular to the y-axis. Such that the height is 3 times the length of the base in region R. So I want to be perpendicular to the y-axis with the height popping out of the page that is 3 times the length of the height that is in the page. Okay, so we know that our infinitely small side must be a change in y since we're perpendicular to the y-axis. The trickier part. What is this length that's inside region R?
It's x.
It's x, so it's our x value right now. I do need an equation for that. So this equation for the curve is y equals 2 root x. What happens if you solve for x?
X equals y over 2 squared.
Okay, so that's y squared over 4. So I have y squared over 4 for this side that's in the xy plane, and the side popping out of the xy plane is 3 times that. So that'll give us 3y squared over 4. So what's the volume of our shape?
Y squared, 3y to the 4th power over 16 times dy.
Perfect. And then I'm going to integrate from what to what?
From 0 to 6.
Awesome. We're integrating in terms of y, so we'll go from 0 to 6. Okay, I do need to write that first step we did, solving for x, down here in our answer sheet. So this would be y is equal to 2 root x. Therefore, x is equal to y squared over 4. And then our volume is going to be equal to the integral from 0 to 6, you told me, of 3y squared over 4 times y squared over 4 times dy. Or, like you told me, 3y to the 4th power over 16 times dy. Okay, do we need to solve this, or do we just need to... Nope, right but do not evaluate, so we're set. Okay, I think I'm going to break convention and we'll check the scoring guides just to make sure that we're okay. And I'll keep doing that as we go so you can see how things are scored. So let me throw this over to the left side for a second. We'll see what our scoring guides say. Session 8. There we go. Okay. So I've got 1 point for the integrand, 1 point for the antiderivative, and 1 point for the answer for part A. Our integrand is our setup. So we're going from 0 to 9 of 6 minus 2 square root of x. It's the same thing as x to the 1/2 power times dx. So we're good. Antiderivative, what happened when we integrated? So that's 6x minus 4/3 x to the 3/2. Okay. And then integrating from 0 to 9 should give us 18. Looks good. Then for part B, we've got 2 points for our integrand and 1 point for our limits and constant. Our limits are our bounds and our constant is pi. So I've got pi times the integral from 0 to 9 would give the limits and bounds point. And our integrand is this part. So I've got 7 minus 2 root x squared minus 1 squared times dx. That's good. If you don't write your dx, you won't get full credit for that because your volume has to be 3-dimensional, not 2-dimensional. So if all you have are your difference in radii, then you're only 2-dimensional if you don't have that dx. Let's go back up to the picture of our box. If you did not write your dy, then you're only multiplying a base times height, which is an area, not a volume. For the last one was also 2 points for the integrand and 1 point for the answer. So our integrand was here. We were integrating from 0 to 6 of 3 over 16 y to the 4th dy. That's good. I'm actually not sure what they were doing with their separate point for the answer there, but we've got the same work that they have, so I imagine we would get full credit. It's actually a little unusual. Any questions on the scoring guide?
No.
Okay, cool. Let's check the next one. Okay, for the next one, we're given this piecewise function. I'm told that the graph of g is defined and differentiable on our closed interval from -7 to 5, and g at 0 is 5. So they did give us a start point. We were given the graph of g prime. I always try to mark that because I sometimes tend to make a mistake and believe that the graph is not the right derivative. So our graph is g prime, and it has a semicircle with 3 line segments. The first thing I want to do is find g at 3 and g at -2. So how can I find g at 3 if we know the start point?
Add the area to the start point.
Okay, I'm going to add the area to the start point. So my start point was g at 0, which is 5. What's the area that I'm adding?
From 0 to 3.
Okay, I'm going to add the integral from 0 to 3. So I'm going to integrate from 0 to 3. I'm going to write my general form instead of just writing the areas first, just in case that's worth a point. So I'm going to integrate from 0 to 3 of g prime of x in terms of x. Actually, I might do the same thing here. So this will be g at 0. And then I'll come back and plug that in as 5. So g at 3 is equal to 5 plus our integral from 0 to 3 of g prime of x. So this first part is a semicircle. So how much is the area inside here?
2 times just pi.
Just pi, perfect. So this is pi times 2 squared divided by 4 is just pi. And then what about our area for the first half of this triangle?
3 over 2.
Cool. So that gives me 5 plus pi plus 3 over 2. Or g at 3 is equal to, what would I get if I had a common denominator?
Um, 13 over 2 plus pi.
Cool. I'll have to check later in the scoring guides. I probably would have put that as 13 plus 2 pi over 2. But we'll check later and see if they left it this way. I'm not really sure, actually. Okay, so that was g at 3. They also asked for g at -2. So we're going to do almost the same process. So starting at g at 0, but then I need to add the integral from what to what in order to get to -2.
From 0 to -2.
Perfect. Okay, I need to go from my start point, so I do need to start at 0 and go to -2, which is weird. Since I'm going to have to turn right back around and flip that integral. So g at -2 was equal to 5. If I change the bounds of an integral, that will change this from positive to negative, so I'm subtracting the integral from -2 to 0. So that'll give me... if I scroll back up, what is this area?
Pi.
Also pi. So that gives me 5 minus pi for my area. Okay, any questions on part A?
No.
Cool. Random over 2 here. I'm not sure where that stole from. Oh well. Oh, up here. Okay. So for part B, I want to find the x-coordinate at every point of inflection on this graph, on the interval from -7 to 5, and then explain the reasoning. So if this is already g prime, what do I need to be looking for to find the point of inflection of g?
Find the critical points of G prime.
Okay, I want to find any critical point about which the slope of g prime changes from increasing to decreasing or from decreasing to increasing. So it's almost the critical points, except for a point of inflection, we do have to change sign. So where would my points of inflection be?
0 and 3.
Okay, so I've got 1 at 0, I've got 1 at 3, do I have any more?
Oh, and also 2.
Also 2, perfect. We have to explain our reasoning. So why is 0 a point of inflection?
It changes from increasing to decreasing.
What changed from increasing to decreasing?
The slope of G prime.
Okay, cool. And then I can do the same idea for 2 and 3, so now I just need to write that. So I could say g of x has points of inflection at x equals 0, x equals 2, and x equals 3, as g prime at x changes from increasing to decreasing at 0 and 3. And from decreasing to increasing at x equals 2. Okay, I should probably put a note there. That should be at x equals 0 and 3. Change that really quick. At x equals 0 and x equals 3. Okay, any questions on what we did for B?
No.
Cool. Part C. I'm told that there's a new function h, such that h of x is equal to g of x minus 1/2 x squared. I want to find the x-coordinate for every critical point of h, where every critical point of h that is on our interval, and classify every critical point as a relative minimum, relative maximum, or neither, and explain the reasoning. So, if I'm looking for a critical point of h, what am I actually looking for?
The maximum or minimums.
Maximum or minimums. How would I find them?
The zeros of the derivative.
Zeros of the derivative, perfect. So I'm going to derive this function first. H of x is g of x minus 1/2 x squared. So what happens if I derive?
G prime minus x.
Okay, so if I set that equal to 0, then g prime minus x is equal to 0. Or x is equal to g prime at x. So any point where our x value is equal to our slope of g, this should be true and we should have a critical point. So if I go back up, this graph is already g prime. So I want to find all the values on this graph. where g prime is equal to our x value. So let me erase everything off here again. Are there any points where g prime is equal to the x value?
The 2 midpoints of the circle at root 2.
Okay, there should be 2 points on the circle, and you're right, it's root 2, but I will probably have to prove that. What's the equation of this circle?
Square root of 4 minus x squared.
Awesome. Okay, that's because our radius was 2. So if I wanted to do one more step before that, I could say x squared plus y squared, since they're both centered at 0, is equal to 2 squared. And then write that as y is equal to positive or negative square root of 4 minus x squared. So, since we are a semicircle, we know that this will have to be positive. And there should be 2 values where our x value is going to make this equal to our y value. You mentioned 1, so what are our 2 x values?
Root 2 and negative root 2.
Perfect. Okay, so I'm going to go down here and we'll rewrite that part again. So x squared plus y squared is equal to 2 squared. Therefore, y is equal to the positive square root of 4 minus x squared. And if x is equal to plus or minus square root of 2, x equals y. Okay, then I've got oh wait, actually that doesn't work for the negative value, does it? Because at negative root 2, my y value is going to be positive root 2 here. Okay.
Oh yeah.
So actually,
only root 2.
Only positive root 2 is going to work there. Oh. Everything off, I think. There we go. Okay. So only the positive should work here. Okay, are there any other points that we had on our graph where the x value would be equal to the y value? Or
3, 3.
3, 3, cool. Because our y value is g prime, that means x is equal to g prime at 3. So I need to write my conclusion. We need to just prove that they were relative maximums, minimums, or neither. So let me go back. Let's see, we already looked at the whole circle, we looked at the first part here. My g prime would have to be some value greater than 3 in order to be equal on this side. My g prime would have to be some value smaller than negative 2 on this side, which it's not. So these are the only 2 points that will work. I need to know whether each of these points are relative minimums, relative maximums, or neither. So let's start with this first point we have here at root 2, root 2. Would this be a relative minimum, relative maximum, or neither for the point h of x, where h prime is equal to g prime minus x?
It's maximum.
Okay, relative maximum, you're right. So this is a relative maximum because on this interval, g prime of x minus x is positive. And on this interval, g prime of x minus x is negative. What about this interval on this side? So after 3.
Y equals negative 2x minus plus plus 9.
Okay, I'm looking for these values where x is greater than 3. For these values where x is greater than 3, so at any point after 3. So let's pick a point. We'll say at x equals 5. At x equals 5, what is g prime?
Oh, negative 1.
Negative 1. So that would be, at this point, negative 1 minus 5, which is negative 6. So for this interval, am I positive or negative?
Positive.
Okay, I'm actually negative on this interval. Negative 1 minus 5 is negative 6, which is negative. Since I only had one critical point on that interval, h prime at x is going to be negative for this entire interval. So for this interval here in yellow, h prime at x, which we said was g prime x minus x, is all negative. Okay, I'm going to do this in stages then. For this interval here in marking in green, if I do the same thing, so we'll do g prime x minus x for any one of these points between our two red points. So I'm going to pick this point x equals 2 since that's on our graph. At x equals 2, what is g prime at x?
0.
0. So g prime at x minus x would be 0 minus 2, or negative 2. Therefore, h prime at x is negative. Okay, for this interval here in blue, again, I know the only critical points are these two red points, so whatever the slope of h of x is at any point on this blue part, it should be the same sign for the whole blue part. So I'm going to pick this point here at x equals negative 2. So at x equals negative 2, what is g prime x?
Zero.
0. So this would be 0 minus negative 2 is positive 2. So for this entire interval, g prime at x is positive. Okay, do you understand what we did?
Yes.
Okay, so I'm going to go ahead and rewrite it so that I can justify our answer down here. So h of x has a relative... Oh, actually, we didn't answer that, so let me go back up. You told me that our first point was a relative maximum. What about the second point?
It's neither.
Neither, perfect. Why is it neither?
Because it's It's decreasing before it and it's still decreasing after it.
Perfect. H of x is decreasing before and after that point. So I could say h of x has a relative maximum at x equals the square root of 2, positive root 2, as h prime at x is positive on the interval do not include it. Actually, we are included for that first point. So included for... Oh, not included. Negative 7 is not an interval. Okay. From negative 7 to x equals root 2. From root 2 to 3, and from 3 to the end of our interval at 5. H of x has neither a relative maximum nor a relative minimum. At x equals 3, although it is a critical point. And we've already justified that because we're negative on that interval from root 2 to 3 and from 3 to 5. Okay. Any questions on anything from that one?
No.
Okay. See if I can get this back on one page somehow. Alright, I'll leave that for later. Let me jump into the scoring guides and we'll see how we did. Okay, so it says first parts, we needed to use our start point, g at 0 is equal to 5. For both parts of this. And then find g at 3 and g at negative 2, so it's 13 over 2 plus pi and 5 minus pi. Okay, so we're good there. 1 point for identifying 0, 2, and 3 is the points of inflection, which we did. And then 1 point for our explanation, because we were changing from increasing to decreasing and decreasing to increasing. For the last part, 1 point for the derivative, g prime at x minus x. Therefore, g prime at x is equal to x. 1 point for identifying square root of 2 and 3. And then 1 point for our answer for root 2 and root 3 with analysis. That's a relative minimum and neither, with some analysis of what happened to h prime at x. So I think we're good for all 9 of those. Any questions on the scoring?
No.
Okay. We've got time for one more. I'm going to leave it up to you. So do you want to do a separable differential equation one or a curve sketching one?
Curve sketching.
Okay. So I'll skip down to our curve sketching one then. So this is 2005 question 4. We have a function that's defined by this table that we're told is continuous on the interval from 0 to 4. 0 is included, 4 is not. Our function is twice differentiable except at x equals 2. The function for f and its derivatives have the properties indicated by the table above, where d and e indicates that the derivatives do not exist at x equals 2. On our interval from 0 to 4, first we want to find all the values of x for which f has a relative extrema, and then decide whether it has a relative minimum or maximum at those values. So what am I looking for a relative extrema?
I'm not sure.
Okay, a relative extrema is a relative minimum or a relative maximum. So how would I know whether this function has a relative minimum or a relative maximum?
When f prime is 0.
Okay, so this is whenever f prime is 0 or undefined, I have a critical point, and whenever it changes sign, I have either a relative minimum or maximum. Okay, so for us, I'm only going to look at our derivative column, and we'll see if we had any critical points that were showing. So these critical points would have slopes of 0 or be undefined. A relative minimum or maximum would be any of those where we actually change direction. Okay, so our first one, at x equals 1, I do have a slope of 0, so that's a critical point, but it's not a relative minimum or maximum. Why is it not a minimum or maximum?
Because it's the last point. The first point.
First point. My first point's actually here at x equals 0, where my slope was positive 4. At x equals 1, my slope is 0. But what happens around that point to my slope?
The circle bracket means it's included or not included.
Okay, so down here, the matrice means included. The parentheses means not included. So our interval includes the 0, but does not include the 4. If I look just at x equals 1, my slope is 0. But before x equals 1, my slope is positive. After x equals 1, my slope is also positive. So is this a relative minimum, a relative maximum, or neither?
Oh, it's neither because it didn't change sign.
Perfect. Okay, so x equals 1 is neither. Since this is only asking for relative extrema, not critical points, we don't need to include this one. Okay, my start point was at 0. We don't have any information about what happened before that, so 0 can't be it. At x equals 2, our function does not exist. My slope before it was positive, and my slope after it was negative. Okay, our slope did not exist, but I did have a y value. So that means this is not a vertical asymptote, but our slope doesn't exist. What would that look like if we don't have a vertical asymptote, so our function is continuous, but is not differentiable?
Have a sharp turning edge.
Perfect. So we can call that a cusp. Cusp is a sharp turning point. It's a point where we are continuous but not differentiable. So we have a cusp at x equals 2. That is a critical point. Critical points are points where our slope is equal to 0 or our slope is undefined. For critical points, it does not matter whether we change slope. It's still considered a critical point. For points of inflection, when you're looking at the second derivative, your slope must change in order to be a point of inflection. For a critical point, your slope does not have to change. But we're talking about relative extrema. A relative extrema is a relative minimum or a relative maximum, and for that, our slope does need to change. So we have to be a critical point that's either where we are 0 for our slope or undefined, and our slope has to change, either positive to negative or negative to positive. So I do have a critical point at x equals 2 as well, but is that critical point a relative maximum or relative minimum?
Maximum.
Relative maximum. Why is it a relative maximum?
It changes from positive to negative.
Perfect. Okay, I'm going to write that down here since that's the one we actually need. I have f of x has a relative maximum at x equals, what was that x value? X equals 2. As f prime of x is undefined and f prime of x is positive, on the interval from 1 to 2, and negative on the interval from 2 to 3. Okay, what about x equals 3?
It's neither.
Neither, perfect. So at x equals 3, our slope is negative 3, and it stays negative before and after that, so it's also not a critical point. So I'm going to recap really quick. X equals 1 is a critical point, but is not a relative extrema. X equals 2 is a critical point and is a relative extrema because we changed sign. X equals 3 is not a critical point, and therefore not a relative extrema. X equals 0 and x equals 4 are the endpoints of our interval, so they can't be either. Okay, any questions about part A?
So if there is a line of slope 0, the whole line would be consist of critical points, right?
Yes, unless it's a line segment. Then your start point and end point would not.
Oh, got it.
Okay, part B. For part B, they're asking us to sketch a graph that has all of the following characteristics. Okay, so I want to match this table with our graph. What's the first thing you would do you think? What's the easiest part of this to graph?
From 1.
Okay, so start at x equals 1. Okay, I think I would start with just graphing the points. So that's everything I'm highlighting in blue. So I've got 4 points total that I need to graph and make sure that are on the graph. So I'll go ahead and graph those in blue. Let's see, I've got points at 0, negative 1. So 0, negative 1. A point at 1, 0. A point at 2, 2. And another point at 3, 0. Okay. Then I need to look for what happens between these points. So I'll need to know 2 things. I need to know on each interval, is my slope positive or negative? And is my concavity positive or negative? If I am I'll write it this way. Okay, if I'm increasing in concave up, my graph will look like this. If I'm increasing in concave down, I'll look like that. If I am decreasing in concave up, I would look like this. And if I'm decreasing in concave down, I would look like this. Okay, so based on the information from our graph, I'll know how our function is supposed to look. Okay, so first part, here in yellow. Just I'll do it in green because yellow is a little hard to see when I start graphing with a pen. I'm looking at our slopes and our concavities for each interval. So for the first interval, we are increasing and concave down. Okay, I am increasing and concave down on the interval. So it should be curved like that. Okay, for the next interval, I am increasing and concave up. Increasing concave up on that interval. So curving upward. Then I am decreasing and concave down for the next interval. Decreasing concave down should look something like this. Just lost the whole computer there. And then decreasing and concave up for the last interval. Okay, decreasing and concave up. Hold on, from 2 to 3, I was decreasing and concave. Oh, okay, I actually drew decreasing concave up from 2 to 3. That's my bad. Let me go redraw that for a second. Okay, what was here? And then, okay, from 2 to 3 we were decreasing concave down, decreasing concave down. There we go. And then from 3 to 4 we were decreasing and concave up, decreasing concave up. Okay, now it's a little better. So I've got my crazy piecewise function where the slopes don't quite match at x equals 2. And we're relatively smooth otherwise. Any questions on what we did for part C?
No.
Okay, to save time, instead of just redrawing that in the box, I think I'm just going to copy that. So let me...
Oh, actually, should we draw a empty circle for x at 4?
Do we know what's happening at x equals 4? Okay, that's the end of our interval. We can. Okay.
So both kinds of drawing is going to be accepted by AP exam, right?
I don't think they would count off for that, because if we ended our function infinitely close to 4, there would be no way of knowing just looking at your graph whether you dead-ended at 4 or right before it. So I don't think they would count off for it, but if they did ask you to mark it, I feel like it's I feel like it's better if you do include that circle. So I don't think they would count off for it because they didn't specifically ask for it. If you're just drawing the function and you don't mark the endpoint as closed, then there's no way of saying that you were wrong. But I do think your way is better than mine. I think drawing the open circle is more clear for someone who's going to read it.
Got it.
We'll see in the guides later if I'm wrong, but I don't think they would mark you off for it. Okay, for part C, I want to let g of x be defined as the integral from 1 to x of f of t dt on our open interval from 0 to 4. From 0 to 4, I want to find all the values of x for which g would have a relative extrema, and then determine whether g of x has a relative minimum or maximum at each of those values. So if I'm looking for a relative extrema, what do I have to do to g of x?
Derive.
I need to derive and set it equal to 0. When I derive the integral from 1 to x of f of t dt, what will happen?
F of x minus f of y.
Okay, if I derive the integral, that means I would integrate, so I'll get a capital F of x minus capital F of 1, where capital F is whatever the integral of f is. And then I would derive that integral with each of these bounds. So I would get my lowercase f again of x dx with chain rule minus lowercase f of 1 times d1 with chain rule, which is 0. So I'd end up just getting f of x dx.
Oh, so for any number for the lower bound, it's not going to matter, right?
As long as your lower bound is a constant, then it won't matter. If you integrate from a variable to a variable with chain rule, you will have to multiply by the derivative of that variable, but it's always going to be upper bound minus lower bound. So if you are deriving an integral, our general form would look like this. The derivative of an integral from a to b of f of x dx is equal to f of b times b prime minus f of a times a prime. That's because I would integrate this function to get some other function of b minus our new function of a, but then I would derive our integral to get back to f of x. So I'd have f of my upper bound times the derivative of my upper bound with chain rule, minus f of my lower bound times the derivative of my lower bound with chain rule. So the only reason that that last lower bound cancelled was because our lower bound in this case was a constant, and the derivative of a constant is 0. So with chain rule, I'd be multiplying by 0.
Oh, got it.
Okay. Go back. If you ever see second fundamental theorem mentioned on the AP exam, that's what they're referring to. The first fundamental theorem says if you integrate from a to b of f prime of x dx, you'll get f of b minus f of a. So first fundamental theorem, first fundamental theorem says when you integrate, you'll have to plug in your upper bound and subtract your lower bound. The second fundamental theorem says if you derive an integral, you'll get back to the same function, but you'll have to multiply with chain rule, and you'll have to plug in your upper bound minus your lower bound. So second fundamental theorem is a shortcut. You integrate and then you derive again to get this. The first fundamental theorem tells you what happens when you integrate a function in general. Okay. bit of a tangent, let me come back. So we were trying to figure out whether we had a relative minimum or maximum at each of these values. Okay, so we said g prime at x is equal to f of x. If that's true, in order to have a relative extrema, my f of x needs to be either 0 or undefined. So taking a look at our function, are there any points where that could happen?
1 and 3.
Okay, so at x equals 1 we are 0, and x equals 3 we are 0, cool. Which of those points would be a relative minimum, maximum, or neither? So is x equals 1 a relative minimum, maximum, or neither?
It's going to be minimum.
Okay, the minimum because our y value changes for f from negative to positive. That means if our y value is g prime, that our slope of g changes from negative to positive, so we'll have a minimum there. What about at 3?
Maximum. Because it changes from positive to negative.
Awesome. So therefore, g of x has a relative maximum at x equals 3 and minimum at x equals, what was that other value? X equals 1. As f of x changes I'll say as f of x is positive on the intervals that were positive and negative on the intervals that we were negative around those points, and then I'll fill in those intervals. So we were positive on 1 to 2 and 2 to 3. And actually positive on the whole interval from 1 to 3. 2 is included. And negative on the interval from x equals 0 to 1 and 3 to 4. Okay, any questions on part C?
No.
Okay. Part D. For the function we just defined as g, find all values from 0 to 4 at which g would have a point of inflection and justify our answer. So for our point of inflection, we need to be looking at the second derivative. So if g prime is f of x, what is g prime prime?
F prime.
F prime of x. Okay. So where will g of x have a point of inflection?
At critical points of maxima or minimums of f of x.
Okay, at the maximums or minimums of f of x. So that means our only point of inflection is at x equals what?
2.
2, perfect. G of x has a point of inflection at x equals 2, as x equals 2 is I was going to say is a relative maximum, but I guess I'm going to do this with the definition of a point of inflection, so that's a little safer. G of x has a point of inflection at x equals 2 as g prime prime of x changes from positive to negative about x equals 2. Okay. So I'm going to jump into the scoring guides for this one. We'll see how I did. And then we'll stop there for the night. So this is 2005 now. Okay, first part. 1 point for relative extrema at x equals 2 and a relative maximum with justification. Okay. 1 point for having our points at 0, 1, 2, 3. 0, 1, 2, 3. Okay, we're good there. And behavior at 2, 2 as a cusp, okay? 1 point for appropriate increasing and decreasing in cavity behavior. Double check that really quick. Increasing, decreasing, and concavity behavior. Down, up, down, up, down, up, down, up. Okay, cool. Then part C, setting g prime at x equal to f of x, okay. Getting critical points at 1 and 3. And our answer with justification. Okay, x equals 3 and x equals 1, okay. Okay, good there. And then 1 point for getting our point of inflection at x equals 2. Yes, with the justification that we change sign from positive to negative. Okay, I think we're good there too. Any questions on the scoring guide?
For the explanation, do you have to mention about like the theorems, like the first fundamental theorem of calculus?
I think it depends. A lot of times, if they ask you to justify your answer, you can use the intermediate value theorem or the mean value theorem or the extreme value theorem to, and just write those theorems to justify. I don't think they're going to ask you to name this as the second fundamental theorem of calculus unless it's a multiple choice question. But those three theorems, intermediate value, extreme value, and mean value, come up a lot in the free responses proofs. So, if I asked you, why is it that there is a point on this interval where the slope is equal to 0, for instance? If I have 2 points where the average value between them is also 0, and we can prove we're continuous and differentiable, then we could cite the mean value theorem as the reason why. And you might see a point for citing the mean value theorem. Same thing for the intermediate value theorem, so we have to pass through all y values between 2 points as long as we're continuous. Or the extreme value theorem, as long as we're continuous, we will have a minimum and a maximum on that interval. I believe those are the only 3 that I've seen that are actually cited, though, where you have to write down that theorem exactly.
I got it.
All right. Any other questions before we sign off?
No.
All right. Thanks a lot for coming. Sorry to keep you over time.
Thank you.